The point is?
What does the top one do?
This is the point. What's the point?
Ah, and that's
That's
forward
what's
and back. So thank you. So my talk is in the spirit of a developments in first principles theory. And we've seen some beautiful talks since the beginning of this meeting on density functional theory based approaches, which are having such great success. But one has to remember that density functional theory is an approximation to handling the complexity of the many-body problem in materials. And so I'm talking about an explicit many-body method here. Our method is auxiliary field quad Monte Carlo, and I want to tell you about a development that we've made recently, which addresses the complexity of this method compared to density functional theory. In fact, our method pretty much scales like density functional theory if you use a plane wave basis, but there's a huge prefactor. So I'll be discussing today an embedding downfolding method. It's basically a local correlation approach that aims to make applications to larger systems feasible. Oh, and my collaborators are Brandon Esper, who's a graduate student who did essentially all the work here, and Shu Eibang, my collaborator at Carlo and Mary. He's now also visiting at the Flatiron Institute in New York City. So here's an example of a material which we found to be very sensitive to the theoretical level of treatment. This is cobalt absorbed, single cobalt atom absorbed on graphene. It's attracted a great deal of experimental interest, or it did a few years ago. And we considered, one of the questions was, where does the cobalt absorb? Top side, hollow, bridge side, etc. We did some Monte Carlo calculations which unraveled the energy landscape and addressed some of the issues. Density functional theory, as we show, this is a figure from the paper, has difficulty with these different sides. We tested lots of different standard density functional theories, including LDA plus U. Some of them do well for some geometries, some do well for others, but they don't uniformly do well. In fact, this can also be seen in this potential energy curves for the hollow site. The quantum Monte Carlo, so-called exact result, we believe, is given here with the gray shaded arrow bar. The green curve is GGA, and the blue curve is LDA plus U with U equals 4. And the inset shows different LDA plus U calculations with different values of U. You can get it to agree for some absorption sites, but not for them all. So this is just an illustration to point out that we're still working to get more accurate methods. Here's another very challenging system that's attracted a lot of attention recently, and there's lots of materials in this class. This is a single molecule magnet, and it consists of a dysprosium atom, which is bonded to various ligands, and this shows hysteresis, as you can read from the title, and you can see this hysteresis up to a very high temperature, above liquid nitrogen. And one would like to know, so far this has mostly been done with density functional theory modeling to try to understand some of the things that are being seen in the experiment. And this is a very challenging system. It's got 4 F localized electrons. So I'm going to describe a local embedding and downfolding method for auxiliary field quantum Monte Carlo. It essentially gives you an effective Hamiltonian that acts on a much smaller Hilbert space. And I'll show you some applications to kind of a constructed test system that involves titanium atoms terminating carbon chains. I'll try to motivate this in a minute. Here's my only theory slide. So the main thing to know is that auxiliary field quantum Monte Carlo, unlike diffusion Monte Carlo, which most people are probably more familiar with, is an orbital-based method. It's not carried out in real space. And so I've cast it here in a second quantized representation. The first term is easy. That's the one-body term. The second term is the hard term, the two-body term. If we only had the first term, that would essentially absorb all of the density functional type methods. In order to make our approximation, we use this separability approximation, where you partition the Hilbert space into active and inactive spaces, and write the many-body wave function in this fashion. And you can show that the total energy can be achieved using an effective Hamiltonian and a wave function that spans only the active region. And the Hamiltonian then looks this way, and the inactive region only contributes a one-body term. And this leads to a large reduction in the Hilbert space, and you can look at the details in this paper. This is essentially what you do in the superpotential method. The superpotential method can be understood to be exactly the same sort of thing. So here's how our method works. We start with a set of one-particle orbitals that we get from Hartree-Fock calculation or density functional theory, and those are represented on the left. You have the occupied valence, the virtual core, the virtual unoccupied states, and the very tightly bound core states. Then we make a unitary transformation to a localized basis, but we separately localize the occupied and the virtual states, leave the core states alone because they're easily frozen out. And then we make cuts. We introduce a geometrical cut for the virtual space, and we include all localized orbitals that are less than that, and a similar cut for the occupied space, and that defines our red active region. All the states in the inactive region are frozen. So this is essentially like a frozen core type of approximation. This is what you would do in the standard frozen core approximation, and essentially what you do in DFT calculations when you use a pseudopotential. You essentially eliminate the core states from the spectrum. And we also discard all of the virtual states that are outside of this spatial cutoff. And you can tune this to get back the exact result by just increasing these localization cutoff radii. So first I'm going to just illustrate the calculation using a toy model, just looking at oxygen on a 20-atom hydrogen chain and looking at the potential energy curve as a function of the absorption height. These are the results. Let me just talk you through it. On the left, I'm looking at two values of the absorption height, 1.8 atomic units and 3.9 atomic units. So the top family of curve is for the larger height, and the bottom family of curves is for the lower height. The colors correspond to different cutoffs. So of the occupied space, and the horizontal axis is the cutoff for the virtual space. And there's a characteristic feature which is very useful, as we see in these calculations, that when the virtuals start roughly to be equal to the number of, when the virtual cutoff starts being equal to the occupied cutoff, the thing plateaus. And the points on the far right are essentially the exact AFQMC result without any downfolding, any embedding or downfolding. And you see also that although the absolute energy changes by a lot, the difference between for a given cutoff, like the difference between the black curve and the green curves, is very robust. And so when you plot the full potential energy curve now as a function of height, you get very good agreement. And the red curve here is the exact result for this whole range of heights over about 2.5 Bohr range. And this is sort of the distribution of the local orbitals that you get for the occupied and the virtual space. So this is just counting the number of orbitals as you increase this occupied radius or the virtual radius. The occupied is really easy to count. You basically are seeing localized bond orbitals as you go across the chain here. And there's actually two curves, a red and a black curve, for the two different heights. They're separated by about whatever this is, about 2 Bohr, but they're almost indistinguishable except very close here to the oxygen atom. So now we're going to look at a more realistic challenge for this method, and we were motivated to look at carbon chains because of this interesting report that appeared in Nature Materials a couple of years ago. They succeeded in synthesizing very long linear carbon chains, up to 6,000 atoms, protected inside double wall carbon nanotubes. And this is a sort of a picture. These are standing tunneling pictures of the carbon nanotube, and you can see the chain in this picture. So motivated by this, we decided to just concoct this model of functionalizing a carbon chain of a certain length and sticking in titanium at the end and terminating it with a hydrogen, and also terminating the hydrogen at the end. And we were going to model we're not starting off with the nanotube just for the purpose of testing our method. We decided to put this in a graphitic environment, but using just a ribbon, sort of a graphitic ribbon consisting of 56 carbon atoms and terminating hydrogens, and the distance here is adjusted to the experimental distance that was seen in the synthesis that I just described. So we first, I'm going to show you some results for just the chain, the isolated chain. So there's no ribbon inside. This is just a chain in vacuum. And what I'm going to be looking at after we equilibrate the structure at equilibrium, we're going to vary simply the distance between the titanium and the first carbon in this chain, and look at the behavior of those curves as we apply our downfolding and embedding cuts. So here again is a picture similar to what I showed you for the hydrogen. These are corresponding to two different values of this delta parameter. And again, we see this behavior that when the cutoff for the virtual state is about equal to the cutoff for the occupied, the curves plateau and you get excellent cancellation of errors. And so if you look at the differences here, you get very good agreement for the difference between these two different values of delta for these different cuts as shown in the inset. And here's actually a full potential energy curve over this range, and this curve is showing the difference with the largest cut. This was beyond our reach on just local computers. We would have to go to a supercomputer to actually treat the full chain of 29 carbon atoms. Now we're putting the chain on top of this graphitic plane. Here's the chain. This time we only used, again, because we just wanted to be able to do all these calculations locally, we're just using a 7-atom carbon chain, but everything else is the same. And we verified that the isolated chain the results are very similar between the 7-atom and the 29-atom carbon chain. And now we have to sort of broaden a little bit the cutoffs for the active and inactive spaces. And so we use the same cutoff criteria for the chain. And in the substrate, we consider different choices of the cutoff radii. And the choices are based on where the titanium atom sits in registry above the graphitic plane. And as we stretch the bond length, this is sort of, these two dots represent how the titanium atom moves. And so we consider different types of localizations in the substrate. And we also, one of the localizations was essentially to make the whole substrate be inactive and then these different things. And again, we find very good cancellation of errors. This is the full potential energy curve. What we're doing is we're keeping the height of the chain above the ribbon the same, and we're just varying the bond length. And this curve is showing, it's a little hard to follow this in this short talk, but this green curve here with the big symbols on it is basically showing that we've essentially converged with respect to these cutoffs in the substrate. The other two curves are basically showing our results where either we're just considering the chain in vacuum or freezing all the states in the substrates. And those are quite similar, but different from the full result in this stretched regime. So I've been hurrying because I usually run out of time, but I think I've been plenty of time today. So this is my summary. I've told you about this local embedding and downfolding approximation that we've developed in auxiliary field quantum Monte Carlo. The relative energies converge very rapidly to the full result in these test systems that we looked at. The rate of convergence is very similar for these related systems, showing that the cutoff criteria are rather robust when you have a kind of a hotspot in the system you're studying. In our case, these chain systems, clearly the region where strong electron correlation is important is around the transition metal atom. We don't expect much difficulty with the carbon chains, and so it's not too surprising that we get good cancellation of errors in that way. The results I've shown you were for a single determinant. This is a technical point, restricted Hartree-Fock trial wave function, which we found often to be very good in quantum Monte Carlo. But we can easily extend this. It's very straightforward to using multi-determinant trial wave functions in situations where the systems are even more strongly correlated. We believe the convergence will be similar to what we're seeing here, since you're just starting with a different set of canonical one-particle orbitals, like natural orbitals or something. We find that the computational effort is greatly reduced by much as 3 orders of magnitude compared to the full AFQMC calculations for these systems, and so this significantly increases the system size that can be feasibly treated with a many-body approach. So thank you.
Have you tested this for spin polarized case?
No, this is we've only done this so far for non-spin polarized. However, these calculations were done for the spin polarized case. In fact, these we considered singlet and triplet states for these different binding sites, but we used the restricted Hartree-Fock wave function. Open shell ROHF type wave function to do that. So we can include spin. We just haven't done it with these calculations.
Very nice. Can you say a little bit more about the embedding? I mean, you've got the frozen lower states are treated with DFT and
Hartree-Fock in this case.
Hartree-Fock, okay.
Yeah.
But then, you sort of have cross terms between the active space and the frozen space. I can imagine there might be issues with overcounting or...
No, there isn't. It's exactly, formally or theoretically, it's exactly equivalent to a frozen core approximation. If you do an atom in Hartree-Fock theory, and you say, well, I'm going to do something with the oxygen atom, but I don't need to include the 1s, or for the titanium, I don't need the titanium 1s, 2p, 2s. So you make a frozen core approximation, and that gives you a Hamiltonian that looks exactly.
So the